Bring up a NIOS. Get the calculation running on the NIOS. Get the Mandelbrot calculation running on the NIOS. Probably control SRAM from a NIOS parallel port or a couple of NIOS parallel ports, and show that you can display a Mandelbrot set using serial calculations off of the NIOS. Once you do that, then you know the video is running, you know how to do the calculations, and you've got the NIOS set up to run. Now you can start offloading some of the calculation work onto coprocessors and speed it up. But at the very least, you'll have it running. So what's the status here? Everybody got NIOS? This is running? Yes? No? Yes? Yes? Yeah? Yeah? Probably. Has NIOS running? No? What's the problem? How come it's not running? Have you run into problems, or have you just not done it yet? That's the question. If you run into problems, so what are the problems? Have you got it running? And it's running? Good. So you could download a program, which means you can, at this point, you can get anything running you want. I'd say the next step is to, I think that the easiest way to get the video hooked up is going to be to display video from SRAM rather than M4K blocks, and to control the SRAM from the NIOS by using a couple of parallel ports, one for address, one for data. There's a bunch of advantages to this. One is that you can run complicated logic on the NIOS without having to program it in hardware. You can use software, which is nice. Secondly, it's pretty easy to build a software queue for pixels if your iterators are bursty, so you get a bunch of pixels all at the same time. It would be nice to have a stack where you can store these before you access SRAM, so you don't slow down your iterators. So I think it's going to be a good idea to set that up first. Any questions about Lab 4 at this point?
I haven't been able to use the C with peripherals. When programming with the Automaton, there's C.
C with drivers or whatever it's called, yeah.
And whenever I download the file just in the C, it works and it downloads fine. But when I change it to C with drivers, it says it doesn't fit, or sometimes there's an error. The same like with the SRAM clock signal. It's the same error.
Doesn't fit.
It says it doesn't fit. It gives me three options. It doesn't fit, or the synchronization problem with the memory.
Are you using? But you're not using SDRAM. Is it SDRAM? Okay, so and you build a phase lock loop to delay the SDRAM 3 nanoseconds or whatever it is.
Yes. And I downloaded the file with SDRAM with the C program, and it works fine. But if I change it to C with the drivers, it says it doesn't fit.
Doesn't fit. Because if you're actually loading the program to M4K blocks, I could believe that. But the SDRAM is gigantic by the standards of the drivers. So I guess I'll have to see that. I have to tell you, I didn't do the tutorial. What I did was take one of my old projects and rerun SOPC builder for the Quartus version 11 system, then reran Quartus, and then opened up the Accelerometer, linked up the PTF and the SOF file, and opened the C source, or compiled the C source that already existed, and it ran. So it works so easily that I don't know what causes the bugs, right? Because I didn't exercise those failure modes. This morning I was trying to see if I could get 2 parallel CPUs running using the Accelerometer, and Accelerometer does not appear to like that very much. But I may not have been doing it right, so stay tuned on that one. So I don't know what the answer is, but let's look at it in the lab. Maybe we can figure it out. Like I say, it worked with my code and it worked easily, so I said I'm done. What other aspects of Lab 4? Okay, so once again, I'm going to ask you what you want to hear about for the rest of the semester. And if you don't tell me, then I'll just talk about whatever I think is most interesting at the moment. But it would be nice to talk about stuff that is relevant for final projects, or of which you have some general intellectual interest. So I prefer the feedback. And one way of doing that is to find out what you're going to do for final projects. So again, I'm going to ask people to tell me what you're going to do. You only got about another week and a half to figure this out anyway. So you should have been talking about it by now. So what are you going to do?
My partner had an idea with respect to signal processing, image processing on the board. But
which was? Oh, biomedical signal processing. Yeah, that's a good idea. Where you hook up to a data bank or to a human if you're brave, and then try and do real-time pattern recognition of the ECG or some other pattern. Yeah, I think that's a good one. That's got a lot of room for using up cycles and for doing sophisticated analysis. Terry?
I'm still interested in the karaoke machine that gives you a score at the end.
Karaoke machine.
Yeah, like you're comparing like the pitches of 2 singers.
So do the signal subtraction to get rid of the voice, or
I should keep that voice to compare it.
Right. And so there's interesting aspects of this. One is pitch extraction. Now, how do you do pitch extraction from a voice? And clearly you can do it in the time domain or the frequency domain. If you Fourier transform voice, so you have f in this direction and amplitude in this direction, you get a really messy looking thing, because the pitch of your voice is around 100 to 200 hertz for most people in the room. And the resonances of your throat have a bandwidth of 400 or 500 hertz. And the first resonance is at about, probably 200 or 300 hertz. And the waveform is not a pure sine wave, even if you're saying, oh, it's not a pure sine wave, but rather something like this. The driving waveform comes from your vocal cords slamming together. So every time they slam together, there's a transient so that this approximates a sawtooth. Anybody remember what the spectrum, power spectrum of a sawtooth is? Does it have odd or even harmonics or both? Is it symmetric about this line? No. Therefore, it has even harmonics. In fact, it has all harmonics, and it has a discontinuity. Whenever you have a waveform with a discontinuity, it says that the waveform can drop no more slowly, no more quickly, than 1 over n, where 1 is the n is the frequency. So the spectrum has to be at least this large. So there's going to be a series of lines that drop no more slowly than 1 over n, or no more quickly rather than 1 over n, and correspond to all harmonics. That then is driving a resonance system that looks like, actually that's even too sharp. The resonances in frequency look more like this. And the top resonance can go as high as 3,000 hertz or so, but not usually that high, more like 2,300 or so. So the range of these resonances is from 300 to, say, 2,300. And there are typically 3 or 4 or 5 dominant resonances in everybody's speech. And these are referred to as formants. So, if you just filter for maximum energy to find the fundamental, what do you get? You're liable to see energy that looks like this. So what's the fundamental? And another way of looking at it is that you kind of sight across all these lines and you try and guess the spacing of the lines. And if you can guess the spacing of the lines, that must be the fundamental. But filtering for maximum energy won't give you the fundamental. Now the problem is that some of these may not be very big and in fact may be lost in the noise. And so you may say that some of them have a spacing that looks like this because that one's really lost in the noise. And so you have an ambiguity there, although you can probably figure out a way around it. Another way that is used is to do a time domain system, because a resonance like this from a driving waveform implies that the output must be impulse-driven decaying sine waves. So if you can find a pattern in the time domain that looks like this and go from large peak to large peak, that's the fundamental frequency. So some sort of cross-correlation scheme, or autocorrelation scheme really, some sort of autocorrelation scheme looking for peaks in the autocorrelation may be the best way to get the pitch. I don't know how Rock Band does it. Be interesting to find out. Video game. So what you want to search for is pitch extraction. For voice. and to figure out what kind of an algorithm to use for that. What are you going to do?
Might do the game of life.
Pardon me?
The game of life.
You do game of life. Cool. So I'd suggest in this one then take a look at Skylar Snyder's Automaton from last year, because he figured out a way of pipelining the video so that he could do a real-time pixel update. For every pixel that was displayed, one cell update was done. That means that the system is completely real-time at video rate. So he was getting 60 updates a second, independent of the screen size. And then the next piece of it, once the updates are going, is to figure out how to load patterns into it. What's a human usable way of loading a pattern into it that might have several hundred active cells? Got any ideas for that?
Not yet.
Not yet. Yeah. So, pardon me?
It's probably started out as hard coding.
Well, you start out as hard coding, of course, for testing. You hard code a glider gun and go from there. But in the end, it would be nice to have it interactive, because I think that just getting the automaton running is going to be fairly easy. But getting the getting the interaction so that it's usable is going to be interesting. Maybe it should import stuff in BMP format. You know, some easy graphic format. Something like that.
I told you, I'm playing Frogger with a Roomba.
You told me that? I don't remember. Playing Frogger with a Roomba.
So I'm going to use a laser rangefinder to let someone come this robot figure out if there are people in its way.
Yeah.
So we can navigate around them.
Okay. All right. Yes, you did tell me. Okay. And what part does the FPGA have in this? Doing the range finding? Because you need high bandwidth to get the rangefinder. Okay. Oh, that's right. Yeah. You better get an idea this week. Yeah, you should, because 2 weeks from now, actually a week and a half from now, you have to start on that. And it's going to be a 5-week project, and 5 weeks goes by amazingly fast when everything goes wrong. You two are partners, right? No. What? Yes. Okay. Also karaoke? But you don't want that. What do you want? Sure, you can use whatever you want. We have cameras. We have microphones. We have op amps running out of both ears. We have any reasonable electronic component you want. We've got accelerometers, probably still. Yeah. Some things are easier than others. Hooking up a television camera to the board is dead simple. It makes a really nice sensor. But what kind of sensors did you want? What kind of motion sensor? A Wiimote? Wiimote sensor. So the only systems I've seen that used Wiimote successfully had a couple of steps. One was to grab the signal and pass it through a Macintosh and then out and through a Bluetooth connection to the Mac and then out through some sort of third-party software that goes to the FPGA, and it was gross. But a what? Wireless mouse. So you could have accelerometers on wrists, for instance, which gets the instantaneous acceleration but not the position. So you can reasonably get speed of motion or acceleration of motion, but you can't get position. Do you need position? Yeah, you can use acceleration to calculate position, but it doesn't work very well. Because it requires a double integration, which is noise, tends to accumulate errors with time. So if you have a transient motion like that, you can expect to integrate the acceleration, double integrate the acceleration over time and get an approximation of how much the position has changed. But while you hold your hand here, the apparent position is now going to drift because of integration errors in the accelerometer. Also, you have the problem of when your hand is like this, if you have an accelerometer axis like this, your hand is accelerating at -1 g all the time because we're in a gravitational field. You turn your hand this way, the acceleration along that axis is now 0. So how do you compensate for the effects of gravity on the accelerometers? Need a gyro so you can get angle rotation. But getting position from acceleration is quite hard. Can be done. Requires temperature compensation. Requires active control of errors. So unless you have a very short-term goal, like figuring out how far you're walking from heel strikes, which some pedometers do. The heel strike is a big acceleration that allows you to reset the integration on every step, and so you don't get too much drift in that 1 second or so between steps. So if you can do that, then if you can have a reset signal routinely, then you can probably do it. Otherwise, it's very qualitative. But what do you want to do with the position sensing?
Using your emotion to generate some rules, and use these rules to do some automaton.
So use those rules to build an automaton. Ooh, that's abstract. So, interesting idea. I'm having trouble figuring out how you would map that in some way that makes sense to a human. I mean, I'm puzzled by what it would do. I'm not against the idea. I'm just puzzled by what it would show. Controlling an automaton from music, setting the rules for music, or using an automaton to generate music might be interesting. Controlling an automaton by motion. Cellular automaton? Were you talking about a cellular automaton or a robot? A cellular automaton is like Lab 1. So some sort of I'm having trouble figuring this one out. I don't see how it's awfully abstract. It's interesting, but it's abstract. Maybe do some Google work on that. John?
Image recognition on the playing cards.
Oh yes. So this is flat up image image processing, fast as possible. See how general you can make it, how fast you can make it. Yeah, okay. So it's possible some talk about image processing could be useful. Do you know about convolution filtering and that kind of stuff? You do. All right. So maybe it wouldn't be useful, but convolution filtering is quite fast on this architecture for the obvious parallel reasons. What you guys want to do?
We were thinking like still that LED audio visualization
Okay. So what do you want to hear about? What do you want to hear about? What would you like me to talk about? I can talk about software radio. Talk about more about multiprocessors on this architecture, NIOS multiprocessors. It's actually not too long a topic. Could talk about simulating a computer graphic pipeline, or doing a computer graphic pipeline, parallel ray tracing for computer graphics. What do you want to hear about? It's all interesting to me. I'm willing to spend some time whipping up lectures, but you got to tell me what to talk about.
Any way to like hook up the FPGA to like external storage, like maybe a hard disk?
Sure. Yeah, actually, there. If you look in there's a recommended textbook for this course, Hamlin's book. If you look in the last chapter, it talks about bringing up Linux on this board. Frightening thought. But he hooks up a external hard drive to the device. That'd be interesting to do. Were you thinking of a IDE drive or a SATA drive or flash drive, or what kind of drive?
Because this year I was like thinking of doing like a prime number finder, so it requires like storing a very large arrays of primes that you have already found in the C.
So you're going to do a Civ of Eratosthenes?
Yeah, something like that. Because since like people seem to be very interested in finding primes.
Well, people certainly are interested in finding primes, and primes are interesting to find. A Civ is not the only way to do it, though. But it's a good parallel problem, because you could do lots of divisions at once, or lots of multiplies at once. But that doesn't. So the idea of a Civ or Eratosthenes is you write out all the numbers between 1 and a trillion, and then then you go through and you mark out every other one, then every third one, then every fifth one, and so on, until what's left are the primes. But there's other ways of generating primes, looking for primes. Or you can calculate pi. I think there's a new record today, isn't there? I think yesterday or today, 10 trillion digits. My word. Number theory. 10 trillion digits, yeah, because there's a fairly... Is there ever a repeating pattern? The answer is yes. Then people are worried. Yeah? Well, that'd be cool. I mean, are you interested in hearing about that? Or are you interested in doing it? Or
Yeah, talking about it. But I'm not sure of the. I'm not enough research to know what are the needs of the project. Is it possible to implement something like that?
Sure. No, that's a good idea, and it is possible to do. It's been done with in a PC environment with webcam and image recognition, where you look for an ellipse which is in the proximate location of your pupil, and figure out whether the best fit for the ellipse, which gives you some estimate for which direction the eye is looking, and also the position of the eye. And I would say that you can probably get reasonable accuracy that way. Probably, well, I'm guessing it'd be hard to get 100 locations to get 1% accuracy, but getting 5% might be reasonable. That'd be cool. Got some projects. Had a project last year in doing eye tracking, so there's some data online about how to do that. I could also probably talk about that if you want. What else? What else are you interested in hearing about? Eye tracking. And prime numbers.
Something like neural networks. Maybe.
On what?
Neural networks. Learning.
Neural networks.
That might be helpful for the ECG.
So, yeah, so you're thinking more of neural classifiers.
Yeah. How do you identify a particular pattern?
Okay, I think I can come up with something on that, yeah. I've played around a lot with spiking neural net, which is how we work. You have impulses running around, and it's the relative timing between impulses that matter. But most neural classifiers don't work that way. They work by some sort of nonlinear thresholding of continuous functions. And I can probably come up with something on that. Well, that gives me some ideas. Gives me an excuse to read up on prime numbers and other stuff, so I'll try and whip up something along those lines. Well, let's talk a little bit about multiprocessors, NIOS multiprocessors. Could be relevant for this project because it's fairly easy to set up communication between two NIOS processors. And you can imagine that sharing the Mandelbrot computation across them might be fairly straightforward. And the Avalon bus supports a multi-master protocol, so you can have several bus masters. And there's really only a couple of modules that are supported very well by multiple CPUs. One is a hardware mutex. This is not a software construct, and it has nothing to do with a multitasking operating system. It's a strictly hardware mutual exclusion operator, so that in one atomic operation, a CPU can say, I want a resource. Give me this. And if it's available, it takes it, and then nobody else can get it. So it's a way of locking out a resource so that only one processor has access to it at a time, and that processor gets to keep it until it's done and releases it. And then the other construct which is available is a mailbox. And again, this is a hardware construct. It consists of a chunk of memory that you specify, either M4K block or SD-RAM or whatever it happens to be, that is shared between a couple of NIOS 2s. in the full configuration, you excuse me. In the full configuration, each mailbox is a FIFO stack, so that you can asynchronously push results into it and pop results out of it. Nice for synchronization between two processors. And these are available on the SOPC builder list, and easy to just drop onto the SOPC builder. I believe that you attach both of these to the data bus. Both of these get attached to the data bus on the Nios 2, on all of the Nios 2s. There's some limitations, or rules anyway. Each processor has to have its own address space. That kind of makes sense. You can't have CPUs executing out of the same code. And, well, maybe you could. And this can be disjoint, so it could be M4K blocks, could be completely disjoint. Or it can be shared SD-RAM. And if it is shared SD-RAM, then the reset vector for each processor determines the lowest address that that processor has access to. So the reset vector, it now becomes the base address. So, for instance, if you had 3 processors, CPU 1 might have a reset of 0x0, which implies that its exception vector is going to be exactly hex 20 higher. So it would be 0x02. And CPU 2, so CPU 1 has all this space. CPU 2 then might start with a reset vector of 0x100000, and an exception of 0x100020, and would have access starting at that address up until CPU 3's reset address, which might be 0x200000. So clearly, if you're sharing SD-RAM, there's going to be a serialization, there is going to be a bottleneck for resource, which is that each CPU has to get code to execute out of different blocks, but the memory is only single access. Now, if each CPU has a fairly good-sized cache, instruction cache, then it may be able to execute out of instruction cache and not have to hit main memory very often. So you may not have too bad a conflict. Another rule is don't share peripherals. Except for mutex and mailbox. In other words, don't hook a timer to both CPUs. I think it will allow you to do that, but don't do it. I already said that these two have to be hooked to the data bus. And oh yes, each peripheral address for each processor has to map into the address space for the processor. So SOPC Builder generates a single module that has all of the CPUs defined in it, and you can include that in your Verilog file. I'm trying to figure out if the Altera monitor can handle the concept of multiple CPUs. My first naive test today failed miserably. It appeared to download the code but didn't start the processors, and I don't know why. So I may be able to fix it. But you may have to go to the Nios IDE, which does support multiple processors, each one of which has to have its own Eclipse project. It has to have its own project in the Eclipse interface with its own board support package and all of the overhead of this big heavy system. But once you get it all set up, it's not so bad. You can edit both CPUs, code for any number of CPUs in the IDE. You save them back to their own projects. When you compile them all at once. Or actually, you compile on a project by project basis, actually. And then you download them all to the board and run them all. Yes, there is a SOPC Builder entity that you want to add which is a CPU ID module. I can't remember if it's on SOPC or part of the CPU ID description, but you want to make sure that the CPU IDs are set up so that each CPU you define has a unique ID, because both of these guys will use the ID which is picked up from the CPU ID module. I haven't done too much with this. I've written a couple of programs. It works. I think that running a couple of copies of a Mandelbrot generator would be a reasonable thing to try. I'll let you know if I get the Altera monitor running with multiple copies of the CPU. Otherwise, you'll have to go to the Nios IDE. Does anybody intend to use multiple nios's? Or were you going to go for the hardware iterator kind of thing? Well, I'll try and get, like I say, I'll try and get the parallel stuff running in the Altera monitor. Yeah, I mean, just like everybody else, I tend not to read the manual unless I absolutely have to. So I guess I better go read the manual and see if it's supported. That'll probably tell me how to do it, actually. Or tell me it's impossible. So any questions? Do you want to hear more about Nios ID, about multiple Nioses, or is that a side show that you don't care to hear more about? Your choice. Write me some email. Okay. 2 groups now at least have tried the DE2-115 boards. Any comments on them? Easy to use? Yeah, just no problem. You got there's a setup program that comes off of the disk that's with them, and it sets up the header file and does so does all that stuff. Okay. I need to get that onto the website, and I haven't done that yet. Since the DE2-115 has about 4 times as many logic elements on it, and something like 10 times as many multipliers, maybe more, 450 multipliers, that sound right? Anyways, let's make it that if you use the DE2 for this lab, your design should go at least twice as fast. And I'm not going to scale it directly with the number of logic elements, because there could well be a serial bottleneck that limits performance independent of the number of iterators, although I don't think so. Yes, a cool final project, or maybe even on this project, although I don't expect it, would be to get the Mandelbrot update rate up to animation rate. Last year the maximum rate was about 1/4 of a second, half a second, 0.4 seconds, about half a second. If you could get it another factor of 5 faster than that or so, get it up to better than 10 per second, then you could zoom in real time, zoom in at animation rate, zoom out at animation rate, and then the nature of the controls will be much different, where every time you press one button you zoom in 1%, or however, a few percent, or you zoom out a few percent, or you pan left or right a few percent. That could be a very cool implementation, or even probably a final project if you got it up to, particularly if you got it up to 30 frames a second. If possible. Okay, I will try and whip up some stuff on eye tracking, prime numbers, and neural networks.